Hello everyone, my name is Florian. I'm a PhD student at Ghent University. My talk today will be about a novel type of electric radiant panel that we have developed within the Structural Fire Engineering Research Group at Ghent University, and we call it the High Intensity Fast Response Electric Radiant Panel, or HIFREP in short. To give you a bit of an introduction, this is the Manuel van de Putte laboratory at Ghent University. It's a traditional structural testing laboratory, and we can do many cool things there, but the one thing we cannot do is fire testing. And as you can see, it's a big space, but it's filled quite a lot already. So we also don't really have the space to put like a big furnace and an exhaust hood and so on. But we still want to do fire tests on structural elements of mainly non-combustible materials. So we decided to look into bench scale devices, and we ended up with a radiant panel. Now, because we're interested mainly in non-combustible materials, we started looking into electric radiant panels, to be precise, because that would avoid the need for having to install an exhaust hood, for example. Now, in literature, you can find some examples of electric radiant panels, but rather than just blindly copying such a design and implementing it in our own laboratory, we decided to take a step back and to actually come up with a completely new design, which is then of course the high intensity fast response electric radiant panel. Now, in some key features, we can say that the HIFREP is fully electric. There's no combustion whatsoever, and as long as you don't expose any combustible materials, there will also be no combustion, so you don't need to have an exhaust hood, so it's suitable for a traditional structural testing laboratory. It gives us quasi-instantaneous control over the thermal boundary conditions. It can easily be flipped, so it can be used both in horizontal and in vertical position. It has an integrated feedback loop, which gives us even better control over the thermal boundary conditions. And it has a heating area of 700 by 500 millimeters, which is, of course, at the panel level. The core of our panel looks something like this. So we have a steel frame, a small steel frame, onto which we have mounted some components. Most important ones are at the bottom. There we have the stainless steel module, which houses the infrared emitters. And in front of the emitters, we have a protective quartz glass plate, which has a double function, to which I will come back in a second. The panel itself can create high heat fluxes, but it is supposed to remain relatively cold during operation, because otherwise electrical components could get damaged. So we need a cooling system. In this case, we have an air cooling system, so we have a supply fan. We actually have two, one on the front that's indicated and one in the back that's a bit hidden on this picture. We have two aluminium flexible pipes through which the air is transported. It enters the stainless steel module, flows through a perforated steel plate to get a more even distribution of the air, and then it flows over the emitters to cool them. And lastly, it impinges onto the protective quartz glass plate. Now, this protective quartz glass plate, as I said, has a double function. First of all, it's going to protect the emitters from mechanical impact, for example, spalling of concrete during a test. But it also serves another purpose, because it is going to protect the exposed surface of our specimen from the airflow of the cooling system. If it wouldn't be there, it would directly impinge onto the exposed surface, creating some convective heat transfer, which is much more difficult to characterize and quantify than the radiative heat transfer that we get from the emitters. So in that sense, it avoids this convective heat transfer. The most important part of our panel are the emitters. We have 21 emitters, which are basically quartz glass tubes in which there are two heating filaments, which are very thin wires made of tungsten material. And because the wires are very thin, they have a low thermal inertia, and that's also what gives us the quasi-instantaneous control over the thermal boundary conditions. The wires are 700 millimeters in length, but the part that's actually radiating is only 500 millimeters in length. We wanted to get an idea of the spatial distribution of the heat flux that we could expect from the panel. So we did a calibration. We actually did measurements in a grid of 6 by 4 measuring points over 1/4 of the panel. And we did this at 4 different distances, at 5, 10, 15, and 20 centimeters from the protective quartz glass plate, which means that we have 96 measuring points in total. To do these measurements, we always started from a cold situation and we turned the panel on only for a very short period of time. And we did this for two reasons. If we would have a longer test, then the protective quartz glass plate would heat up. This heating of the protective quartz glass plate would result in an additional heat flux. Well, actually, it's not really an additional heat flux. It's just that when it's cold, it's going to absorb some of the radiation. And when it has heated up, it's going to emit this additional radiation again. The second reason is that we wanted to avoid the surrounding environment heating up, because this could lead to convective flows also over our heat flux gauge, which could alter the measurement. So we decided to go for short durations and actually measure the radiation that we could get from the panel at the beginning of the test. Now, with these measurements, we were able to construct heat flux maps using symmetry. So we did measurements over 1/4 of the panel, and then we kind of mirrored these measurements to get heat flux maps for the entire panel. We did some additional measurements to verify that this assumption was correct, and it appeared to be the new measurements appear to be very well in line with the original measurements. What I would like to highlight here is that at a 10 centimeter distance and at maximum intensity, so 100% intensity of the panel, we can reach a heat flux up to 92.5 kilowatts per square meters. If we go closer to 5 centimeter distance, for example, it can be even higher. Then we are talking about 105 to 106 kilowatts per square meter, but the exposure would be less uniform. Now, talking about uniformity, in the discussions with the manufacturer of the panel, we said that we wanted to have a zone of 70 by 30 centimeters in the middle of the panel, which is indicated by the cyan rectangle, with a uniform heat flux. Now, based on the measurements that we did, it appears not to be fully uniform. There are some gradients, especially near the edges of this rectangle, but so far we have not seen a big influence of this non-uniformity in the tests that we have performed. Something that we're really proud of regarding the panel is the very fast response, the quasi-instantaneous control that we get over the thermal boundary conditions. And we actually wanted to quantify this. So we decided to calculate the characteristic times of the two main components that are radiating, which are the emitters and the protective quartz glass plate. To do this, we came up with a very simple experiment. We turned the panel on at 10% intensity. We didn't start from 0 because the code has some built-in delay, which we wanted to avoid here. So we turned the panel on from 10% to 10%, and then we quickly increased the intensity level to 90%. As you can see, the heat flux that is measured by the heat flux gauge first increases very quickly, which is due to the emitters. It's simply too fast for the protective quartz glass plate to have heated up already. But then at some point, it goes much more slowly. So the emitters have heated up completely, and then it's the protective quartz glass plate which is going to heat up over time. Once we have reached a more or less steady state situation, we turn the panel off completely and we get something very similar in terms of behavior. So first, the heat flux gauge reduces very quickly, which is because the emitters are cooling down. And then there is this very gradual, slow reduction in the heat flux, which is then the quartz glass plate that is actually cooling down. And based on these measurements, we were able to calculate the characteristic times. We found for the emitters that it's around 1.7 seconds. Depends a bit on which data points you take into account, but it's always order of magnitude seconds. While for the protective quartz glass plate, it appears to be around 427 seconds. So at least 2 orders of magnitude higher. Which is a bit of a problem because I was claiming that we had quasi-instantaneous control over the thermal boundary conditions. So we had to find a solution for this problem. And we found the solution by adding a feedback loop to the system, which in effect is going to act as a PID controller. So what we have is a Python-based controller. It's just a Python-based graphical user interface that we have developed ourselves, which is going to give an input voltage to the panel between 0 and 10 volts. That's just for clarity, not the voltage at which the emitters are actually operating. This is just what we give as an input to the panel, and then the panel is going to produce an output, and the output in this case is thermal radiation. This thermal radiation can be measured with the heat flux gauge, and if we use the heat flux gauge measurement again as an input for the Python-based controller, we can actually adjust the input voltage to reach a predefined target heat flux. And this is very good for two reasons. First of all, it's a self-adjusting system, so it's going to give us an even better control over the thermal boundary conditions. But secondly, it also allows us to bypass the slow response of the protective quartz glass plate. Imagine that your quartz glass plate has heated up because you're conducting a long test. Then you can just simply reduce the input voltage a tiny bit, reduce the intensity of the emitters to actually compensate for this effect. And with this feedback loop in place, you can do quite cool things. At some point we tried to follow a sinus function. So what you can see is that in the beginning the system is stabilizing, but once it has stabilized, it actually manages to follow the target heat flux curve quite well. And also the time scale that we are looking at is only 100 seconds, which means that we actually have a very fast control over the thermal boundary conditions. Okay, so I think this was enough about the panel itself and its different components. Let's take a look at how it really performs through an application example. So what we have here is a reinforced concrete beam that is placed in a reversed 4-point bending setup. And we have the middle part of the beam that's heated to the middle 70 centimeters. Just some details on the beams. They are 29 by 20 centimeters. There are 5 rebars of diameter 16, 3 in the tension side, which is the top side in the reversed 4-point bending setup, and 2 in the compression side. We have a concrete cover of 20 millimeters, which is for the main rebars, not for the stirrups. We have a design value for the resisting moment, which is 72 kilonewton meters, and cracking occurred at 10.13 kilonewton meters. We were conducting temperature measurements during the test through thermocouples that were placed inside the beam during casting. We were doing them at 3 different locations, and for each location we had thermocouples at different depths, so we could actually get a temperature profile at a certain time instant. Now, in terms of results, what I want to show you are the temperature profiles over multiple tests and the residual capacity. So for the middle position of the thermocouple 3, we took the measurements for the 3 beams that we tested. So I forgot to tell you, but we are testing 3 identical beams. So we took the average of the 3 tests, which is the real line that you can see in the plot on the left-hand side of this slide. And then we have some shaded area around it, which is an indication of the spread that we get over different tests. And what you can see is that the spread is actually really low. Now, if we assume that the beams are identical, they're not completely identical because concrete, for example, is a whole heterogeneous material and so on. But for now, if you assume that they are identical, then we have the only source that could affect the results is the fire exposure that we are applying through the radiant panel. But because the spread is really low, it means that we have a very high degree of repeatability and that we must have actually a very good control over the thermal boundary conditions. Similarly, for the residual capacity, we first tested a reference beam, which is again the same beam, but it is not heated, and it has a bending capacity of 82.6 kilonewton meters. And then we have beams B1, B2, and B3, which are fire tested, of course, due to the fire exposure or the exposure to high heat fluxes. There's a small reduction in the bending capacity, but what is really important is that the values are really close to each other, which is again an indication of the high degree of repeatability that we can actually get with our radiant panel. Now, to conclude, some final notes. So within the Structural Fire Engineering Research Group at Ghent University, we have developed a fully electrical radiant panel that gives us quasi-instantaneous control over the thermal boundary conditions with very well-defined heat fluxes, especially through the integrated feedback loop, which is self-adjusting. We managed to get a high degree of repeatability in our test, which is indicated by the application example that I've shown. And with this, I will conclude the presentation. Thank you very much for your attention. And in case you would have any questions or if you have suggestions on how we can even further improve our setup, please feel free to contact me through the email below.